Okay, so now's when it starts getting harder, and we're gonna today is gonna be. I'm gonna try to get a lot done today, so please stay. It's weird. So please stay tuned in. I'm gonna record this. Definitely post the videos today's class. So if you don't write everything down, it's more important that you pay attention, and then you can get good notes later by watching the video. So here we go. Oh, this screen is just too low. That's what it is. I don't know if I can stop it halfway though. Okay, well, I was going to get off to a great start right at start of class today, and of course, something came up. All right, here we go. So we'll just read that. It says, given the vector field negative y over x squared plus y squared and x over x squared plus y squared is our p and q. So first of all, is this vector field conservative? So it's negative y over x squared plus y squared. All right, so we're good over there. And x over x squared plus y squared, and that's our PQ. Remember we said our for vector fields are kind of our standard conventional symbols are going to be P for the x component, Q for the y component. So is it conservative? Who knows? How can we check? So remember we could look at the second partials, right? We could look at the second partials. So that means take Q. That means take Q with respect to X. So that's the quotient rule. And then we can take P with respect to Y. That's also the quotient rule. And if we simplify these, we get negative y squared minus x squared over that denominator squared for both of them. Conclusion? Conservative vector field, right? That means that P and Q are the partial with respect to x and the partial with respect to y for some function, right? Because the second partials are equal. Okay, so here are two loops in that, two circulation integrals in that vector field. And so what do you expect? What do you expect for the circulation, the blue square and the red circle? We're in a conservative vector field. They should be zero, right? So that's what we said. We said in a conservative vector field, in a gradient field, all circulation integrals give a value of 0, okay? So here's the blue square worked out. Don't write this down, but you'd have to parameterize each of the 4 segments, right? And calculate each of those 4 separate line integrals. When you add them up, you get 0. Okay? So for the red one, let's go ahead and do the red one here. So the red one is the unit circle. So we'll take one counterclockwise loop around the unit circle. That means we have to parameterize the path, right? So what is it? So for C2, what is our parameterized path? Anna, what were we saying? Cosine t sine t, unit circle, right? Cosine t sine t. Okay? So notice what happens here. So we're going to do f dot dr. Notice what happens when you do cosine squared plus sine squared, we get? It's Pythagorean identity. So these denominators become 1. So that makes this f real nice. So we're going to go, we're going to go from, t is going to go from 0 to 2 pi. Our f is negative y over 1. So that's going to be negative sine t. And then f sine t is cosine t, right? Over 1. Dot dr. Dr is negative sine t, cosine t. Okay, don't forget how to do line integrals. So we're going to start getting some other complicated stuff here. Lots of different hard problems. Don't forget how to do line integrals. Right, parameterize the path, rewrite our vector field in terms of that parameterization, dot dr. Okay, so what do we get? 0 to 2 pi of sine squared plus cosine squared equals 1. dt equals 0, right? Integral from 0 to 2 pi of 1 dt equals 0. Oh, it equals 2 pi. What happened? I thought this was supposed to be 0. Conservative vector field, closed loop, didn't get 0. Okay, so stay tuned to the end of class to reveal what's going on here, right? So something's going on. Something's not right with everything we've talked about, right? With everything we've talked about, there's something different here. Something's not right. So we have some a bunch of stuff to talk about before we can answer this question of what's going on here. But yes, this is a conservative field. Yes, we have a closed loop. No, we didn't get 0 for that. We should have, according to what we talked about so far. Any questions? Okay, so today we're going to talk about Green's theorem. Green's theorem. Here's Green's theorem. Okay, so just listen. Write down later. So C is a simple means it doesn't cross itself. Closed means it makes a loop, so it's a circulation path. C is a simple circulation path, which forms a region D. And it's oriented so that the direction of C is so that the region is on the left if you were to walk it, right? If you were walking along this curve, the region, the interior of the loop would appear to your left. So is that counterclockwise or clockwise? Counterclockwise, right? Counterclockwise, okay? And then F is a smooth vector field defined everywhere on C and D. And then here's the statement of, then what we have? You have the circulation integral around the boundary, around C, is equal to the double integral over the region of this thing, the partial of Q with respect to X minus the partial of P with respect to Y. Okay, so the circulation integral, what you get when you do the line integral around the boundary, is the same as the double integral of the interior region of Qx minus Py. So we can actually relate that to something you've seen before. Fundamental theorem from Calc 1. So I'm going to take attendance, and I want you to, as I take attendance, you're going to figure out what are the parallels of these two. The first question you're going to ask is, how do the sides match up? So how do the sides match? Do they match left to left and right to right? Or do they match across like this? Left to right and left to right? That's the first question you got to answer. And then once you figure that out, then you look at individual parts and you say, where are the parallels, where are the analogies between these individual parts? You know what? I think I'm going to take attendance later. I'm just going to let you talk about this for about just a quick minute, and then I got something later we can do attendance. So, 2 questions. So, how do the sides match up? Would it be left to left and right to right, or would you say left here to right here and right here to left here would be parallel, would align? And then how do individual components align? So once you get the sides lined up, then now you're looking at more of the details. Okay, get a partner. Everyone's talking to somebody. Just about 1 minute. See what you come up with. Okay. So actually, in vector calculus, there are 4 versions of the fundamental theorem that we're going to cover. This is the first. Okay? But there's always this common theme. They always relate back to the fundamental theorem that you learned in Calc 1. There's a strict parallel to it for all of them. So that's what we want to, this is the first time we're covering that. So, first of all, let's say the right side over here, this double integral. Do you think it aligns with the left side or the right side of the bottom equation? Left or right? Do you care? What do you think? Oh, don't be that honest. Yes, you care. Yeah, I care. All right, what's your idea?
I'll guess with the right side.
He thinks it lines up with the right side. Okay, and the way you can know this is, look, this is, what order of integration is this? It's double integration, right? And what's the order of integration here? Single. And what do we have here? Single order of integration and no integration, right? So the fact of kind of order of integration would indicate that this right side up here, this double integral, would align with the single integral or the non-integral? Single, right? Single, okay? So, and it's true. So both of those what are those about? They're about accumulation, right? Accumulation of a quantity by summing up little bits, right? So both of those are about accumulation of a quantity by summing up bits, right? So in the original fundamental theorem, you're summing up bits and by taking what? The rate times a change in independent. Well, you're doing it the same thing here too, except you're just summing up two-dimensional bits, right? You're summing up little two-dimensional bits. Notice this is rate of change. It's something like rate of change, right? Qx minus py, those are both derivatives, right? So this is something like rate of change, and this is a rate of change function. So each little bit is calculated by rate times little change in your independent variable, whether that's a little interval, like a small change in x, or a little change, two-dimensional change, a little piece of area. Okay? So the accumulation of many bits of a quantity, each calculated as rate times change in independent. Does that make sense? See that? And what's the other side? So the other side is that that accumulation of many bits of quantity is equal to what? Like net change. The net change of a quantity that you can calculate like associated with the boundary, right? So you can get the net change of the quantity simply by taking what? Final value of the quantity minus initial value of the quantity, right? So that's like the boundary of your interval from A to B. Okay, and so that's kind of analogous to, in this region that we have, it's like taking the line integral around the boundary. So it's kind of like the net change when you go all the way around. What's your change around the boundary? So this Green's theorem is a fundamental theorem, and it has all these qualities that the original one that you've learned has. And you need to be able to see that. You need to be able to see those parallels. And then each time we introduce a new fundamental theorem, we'll have this conversation again. Super important. Yeah. Nice and loud. Oh, like continuous. Like there's no, so like if there wouldn't be any like discontinuities in it. Like if you were traveling through it, you wouldn't go any place where there was an abrupt change in your vectors, or there was something didn't exist. Right? So it has to exist everywhere, and then as you move through it, it's like there'd be no like wrinkles. Like all of a sudden the vectors just like totally flip at an instant. Loud or freezing? Which do you pick? All right. Okay, so here's just an overview of the proof of Green's theorem. Okay, so we've got two sides to this, right? We've got the circulation integral. The circulation integral, that's the C, is equal to the double integral of over the interior of this, qx minus py. So both of those sides of the equation can stem from this. I'm going to sum up all these little circulations around little c's delta c. All right, so I'm gonna chop up the interior region, and then I'm going to look at each little piece. I'm going to do a little circulation integral around each piece, and by summing all those up, I can get to both sides of Green's theorem. Okay, so the first way I get to the circulation side of Green's theorem is by looking at what happens when you're summing these up. What happens to adjacent sides? So notice, here's two next to each other, say right here. I'm going to do this little line integral around that, and then I'm going to do this little line integral around that. What do you notice happens? Yeah. Yeah, because on this side we're going up, and on this side we're going down, so that those are going to be equal and opposite parts of those line integrals, so those are going to cancel out. All right, so as you sum up every single little teeny circulation on the interior, and all those interior boundaries cancel out, or those shared boundaries cancel out, what's going to be left? Just the outside where there's no shared sides. Okay, that leads us to the, so all shared sides of elements sum to 0, leaving only the sum around the boundary. And that's the circulation integral around C. Okay, so that's one way to view summing up all these little circulation integrals inside the boundary. The other way is this. So now I'm going to look at just one. And so I have this is C1. That's C1, 2, 3, and 4. And so we're looking at one of these little things, and we've got the vector field. So here's the vector. Say, I'm just drawing F right there for this little part of the interior. And so I'm actually going to evaluate, I actually want to evaluate this line integral around one of these little boxes, okay? Around one of these little delta C's, I want to evaluate that. And so we'll start in the x direction by just looking at C1 and C3. Maybe. So just adding up the bottom and the top, C1 and C3, going to be those little parts of this line integral. Okay, and so basically both of those are going from x to delta x, or sorry, x naught to x naught plus delta x. All right, and so then the bottom is at y naught, so it's going to be, all we care about, since these are horizontal pieces that we're doing line integral for, all we care about is the p. The q is not going to matter, right? All we need is the x component of f, right? The x component of f, so that's p. And so I'm going to add, that's C1 right there. And then C3 is going to be minus, because it's going backwards, so I'm going to take the opposite of p at x and y naught plus delta y, so up at this level here. So again, I'm doing just the top and the bottom parts of this little circulation integral in there. But now if you look at this, what is this? This is how much p changes with respect to y changing. And what's that? This is how much p changes for a change in y. So what is this difference right here, essentially? How much p changes for a change in y? What's that? No, it's how much p changes for a change in y. Partial of p with respect to y, right? It's how much p changes with respect to y. So I can rewrite that this way. So this is going from here to here, from x naught to x naught plus delta x. We can integrate how much p changes with respect to y dx delta y. And that would be the top and bottom parts of this circulation integral. And then the two sides are similar. Do the same thing for the two sides. And you get the integral for the partial of q with respect to x for the C4 and C2. And so then to get the total line integral, you add those together. And so that's where the qx minus py comes from. So this idea of summing up all the little circulation integrals within the region takes us two places. We can show that it's equal to that, and we can show that it's equal to that, and therefore these two are equal. And that's kind of just an overview of the proof of Green's theorem. Okay, any questions on that? And this actually, when we get into looking at vector fields a little more closely, then this concept that we just walked through, we'll revisit this. So we'll have more practice thinking about it. Okay, so examples. So here I want to verify Green's theorem. What does it mean to verify a theorem? To verify a theorem means, what's that? You're going to do both sides and show that they're equal, right? So what are both sides? We got the circulation integral around the outside is equal to the double integral of the interior of this function, the partial with respect to x, dA. Okay, so our vector field is, this is our PQ here, y comma 4x. C is a triangle from 0, 0 to 2, 0 to 2, 4 back to 0, 0. So you guys are experts at line integrals. You're experts at double integrals. So you just got to do the math. So there's nothing here that you haven't done before that you can't do right now if you've learned it. So go. So you're doing both sides separately, and then you're showing, we want to show that you get the same number, and that's what we mean by verifying a theorem. Okay? So you're either making progress or you're getting help. Either making progress or getting help. Or just start as a pair and do it all together, work together. that what you got? Somebody? Anybody? You got all that? You got all that? You agree with everything I wrote? Okay, so at this point, you have to have fluency in this. Like, so this shouldn't take you 20 minutes to do. So it's longer than me, that's fine. Longer than me, you know, I wrote it down pretty fast. But longer than me is fine. But at some point, we gotta, you know, stuff we've done in the past, you've gotta have fluency, or because it's starting today, from here on out, it's gonna get hard. It's gonna get a lot harder. So you've gotta have the things we've done before under your belt. Do you agree with what I did? Any questions? Okay, and what are they both equal? Did anyone solve? Yeah, please. So you're talking about the double integral?
Yeah.
So I'm doing dy dx, right? So I'm going to do bottom to top, and then left to right. So bottom to top, I'm going to accumulate at a typical x, starting at y equals 0 up to 2x. And then I'm going to go, and then all those, I'm going to add up all those, starting at x equals 0 all the way to x equals 2. You good? Other questions? Anyone get an answer? They both should be, yeah, what is it? 12? They both 12? So this should be 12. When we add up those three to get the circulation, double integral should be 12. And that verifies Green's theorem, because we're showing that both sides have the same value. That's what we mean by verifying a theorem. Last chance. Other questions? Okay, now, so there's verifying a theorem, and then there's using a theorem. So in this next one, so this looks familiar from your last exam, the exam 3 review sheet. You computed a line integral by going around the loop, right? Okay, so now I want to find a different way to do this. So now you're going to use Green's theorem. Using Green's theorem means you're not going to calculate the line integral. Using the theorem means you can calculate something else, and then you state by the theorem that it's equal to the line integral. So what are we going to calculate to use Green's theorem to find the value of this line integral? What's that? You said the double integral. Yeah, so using the theorem would mean you don't calculate the line integral, you don't calculate the circulation, you calculate the double integral, and then you declare by Green's theorem it's equal to the line integral. So go. So do the line integral in the easiest way possible. Going to be the easiest way. What's that? dx dy, right? Type 2. We're going to do type 2. So x is going to go from what? Negative y to square root of y, right? As y goes from 0 to 1. Now notice what happened. So when we do this double integral, anyone notice what we'll be actually finding when we do this double integral? Yeah, because we've got this, it ends up, because qx minus py in this case is 1, remember, double integrals find net volume, but if you take the double integral of 1, it's the volume of a solid with a height of 1, which is essentially equal to the area of the base, right? The area of the base. So that's just because of the way this turned out. So when we find this, we're actually going to be finding the area of the base, which will equal the circulation integral by Green's theorem. Anyone got an answer? It's like 5/6 or something? Or 7/6? So that's easy. You can do the math. So what does that mean? That means if we were to work out the line integral now, if we were to go do the line integral around this closed loop, we ought to get 7/6 by Green's theorem, right? By Green's theorem. It's equal to this double integral. And in this case, it's also equal to the area of that region. Yeah.
So this Green's theorem only works in conservative vector fields?
Is this a conservative vector field? It works in any vector field, okay? It works in any vector field. So actually, before we go on to the next example, so just kind of hold on to your thought for a second. Are we good on this one? Any questions? Ask if you got a question. How about this one? I want to evaluate this line integral around the slanted ellipse. X squared plus 3xy plus 4y squared equals 1. So I want to evaluate that line integral. So let's talk about doing it directly. How about evaluating this line integral around this? What would that entail? Parameterizing this? That's what you should be thinking. That entails parameterizing the curve, right? Finding the vector function for the curve. How about that? X squared plus 3xy plus 4y squared equals 1. Nah. Don't want to do that. Okay? So, any other options? Green's theorem. Green's theorem says that that double integral, or that single integral is equal to double integral of qx minus py dA over what? And now we're going to integrate, I'm going to set up a double integral for integrating this region D. How about that? Excited about doing that? Why not? Oh, so Thomas noticed something. What kind of vector field is this? Conservative. Q, because Qx is 2y, Py is 2y. Conclusion? Conservative vector field. And so therefore we're integrating 0. So what's the value of the line integral around the closed loop? 0. Phew, right? We escaped we made an escape there. All right, so here's this question. So Green's theorem, does it work for conservative vector fields? Sure, but what happens? It's just 0. It's just trivial, right? So you just get this trivial case in conservative vector fields. Why? Because in conservative vector field, you go around the loop, you get 0, right? So then that makes sense, because also then Qx equals Py, and you get a 0 for the double integral, you get 0 for the integrand. So it works for conservative vector fields, but it's like the trivial case. So it's a lot, Green's theorem is more interesting in non-conservative vector fields, right? So in conservative vector fields, poof, everything's 0 in Green's theorem, and so it's kind of like, so what, right? But so it's more used, useful, non-trivial, and non-conservative vector fields. Okay, questions on that example?
Is there a point where you would want to use our traditional line integral rather than Green's theorem?
Yes, it could absolutely be where if you have the choice, doing the line integral around the boundary would be easier work than doing the double integral. Yeah, you can have situations like that. So if it says verify, you're working both sides and showing they're equal. If it just says evaluate a line integral, then you can consider using Green's theorem to not do that, instead do the double integral like we did in the last example. And then if it says evaluate, so a question might say, evaluate this for a particular region. Okay, and so that's like taking a sledgehammer and hitting you on the head. Like, look, they're what are they telling you to do? Use Green's theorem, right? So like if they say evaluate this, it's like they're really making it very obvious to you that they're talking about Green's theorem. So consider maybe the line integral would be a lot easier, the circulation around the boundary. But that's something that you have to come up with. But that should be easy, right? This is so familiar and so obviously Green's theorem that if they say evaluate that, you're going to consider looking at the circulation integrals, whatever is easier, right? Whatever is easier to compute. Is that a scratch or a hand? What's that? Yeah, we haven't got there yet. Almost there. We might be able to do it today. 6 minutes, I don't know. We'll see. All right, so let's talk about something called, in the edge of your seat, is that what you said? Yeah, me too. And I know what the answer is too. All right, so here's we got to talk about regions now. So a connected region, the idea of a connected region is that it consists of one piece. All right, so a connected region, connected. Non-connected means, so if that's all one region and it's in two pieces, that's so connected, non-connected. Okay, formal definition, given any 2 points, there exists a path from A to B that lies entirely in D. So if I pick any 2 points in a connected region, there's got to be a path from one to the other that stays inside. And that's for any 2 points. But if it's not connected, then I could pick this for A and this for B. And obviously, I can't get from A to B without leaving the region. Non-connected. Okay? So that's connected and non-connected regions. Next, simply connected. So the idea of a simply connected region is it's connected, first of all, one piece, has no holes in it. That's simply connected. Okay? So it looks like, so this would be simply connected. Simply connected. So non-simply connected means you have at least one hole in it, like this. Formal definition. Every simple closed path in C that lies entirely in D, for every simple path closed P that lies entirely in D, every point enclosed in C is in D. So this is a formal definition here. So every single loop I could make that lies entirely in D means that the interior of that little loop is also all in D. So how is that violated in a non-simply connected region? Yeah, you make a circle. If you make it so that all the circles around the hole violate this, you've got all these points that aren't in D. Okay, so a simply connected region is connected. It's all one piece and has no holes in it. A connected region that's non-simply connected has at least one hole in it. Okay, so let's talk about doing integrals in Green's theorem and non-simply connected regions. So is this connected? Is it simply connected? No, right? It's connected, it's all one piece, but it's got a hole. So how would we do the circulation integral around this? Well, the way you can see this is if you cut it, I'm gonna slice it in half and I'm gonna separate it into two pieces, okay? So I'm gonna cut it in half, separate it into two pieces. And so then the total line integral would be the sum of the two, right? So I would have and again, I want to be walking around so that the interior is to my left. So that means counterclockwise on each separate piece. But then when I add those two together, what's going to happen? If I add up all those pieces, what's going to happen? That's going to cancel out, and that's going to cancel out. Equal in opposite directions, right? Leaving this. So the boundary of this non-simply connected region has two parts to it. And if I'm walking to always keep it on my left, then what about that inner loop? Do I go counterclockwise? It's going to go clockwise to keep the interior of the region to my left. The inside loop will go around clockwise, outside loop counterclockwise. All right, so then if that's my region D, then my boundary is divided up into two parts, C1 and C2. And so the circulation integral is the sum of the individual sides, or the sum of the individual loops, C1 plus C2. And so for Green's theorem, that sum of those two, the sum of C1 plus C2, which is the whole boundary, is going to equal our double integral. Yeah?
Why wouldn't it just be the difference between two double integrals? Like Green's theorem for the whole and Green's theorem for the whole sum.
You could do it that way. It's fine. But it's however you want to do the double integral over D.
Okay.
You could do it directly or, yeah. Yeah, either any way you want to evaluate that. Okay, so if you have a conservative vector field, we know that both sides are equal to 0. Okay, so we saw, qx equals py. But now, what does 0 equal? 0 equals the sum of C1 plus C2. So that means that those two are non-zero and equal and opposite. Right, so my circulation integral for C1 is going to be equal and opposite to C2, and they're both going to be non-zero in order for them, when you add them together, to get 0. Does this make sense? Anybody have a question on that? Okay, so we made it we're 1 minute over, but we can talk about it now. So what's going on now? We've got this one turned out to be 0. This circulation integral turned out to be 0. This one did not. Why not? It was 2 pi. So look at the vector field. It has to do with the vector field. The vector field combined with this particular circulation path. What's that? Yeah. Undefined at the origin, right? This is undefined at the origin. So what should I put here? So there's like an open hole right here. So what happened what about this? If I call this my D here, what about D? What do we call that? Non-simply connected. So when I did this C around this loop, I was going around a non-simply connected region because I got this teeny, itty-bitty, teeny little hole. And so what happened? So when I did this circulation integral, I actually wasn't calculating the whole, C2 is not the whole boundary of that region. What else is there? I'd also have to do what? Clockwise around this itty-bitty hole. So what's the circulation integral clockwise around that little hole? Negative 2 pi. So now I have the 2 pi from the outside circulation, and then actually if I did a little teeny circulation around the hole, that would now comprise the whole boundary, both the boundary of the outside and the boundary of the hole, and now it would equal 0. So now the C outer plus integral for C whole, that equals 0. So everything's good in the universe again. We made it.